So I've done all this stuff in 3 space. We found partial derivatives, we found second partial derivatives. What I want to do now is figure out how to find maximum and minimum values. Now, that's no big deal, you say. Megan, that was easy. We did that back in Calc 1. You're right. If we've got something like this, we take the derivative, we set it equal to 0. It's real easy to get the critical points. There's one here, and there's one down here. Easy peasy, no problem. But what if you have something like this? This is freaky. This looks like Maleficent's hat. I like Maleficent. So I see there's a maximum here, a maximum here, but what the hell is going on here in the middle? I've got a minimum looking at it this way, but a maximum if I look at it front to back. So how do we distinguish this, and how do we find these points? We need all the directional derivatives to be 0 at these points, but we don't want to test all of them because, infinitely many might take a while. So let's see what we can do. Local extrema. What is that? Well, if you have a function of 2 variables, so you've got a surface, this will have a local maximum if there's a high point and everything in the neighborhood around it is below it. And that's exactly what we do in mathematics. We call it a neighborhood. We put a little neighborhood around AB, like a little circle. As long as all the points within that circle have a functional value less than the functional value at AB, then it is a maximum. We say the maximum occurs at AB, and f of AB is the local maximum value. Same thing for minimum. We want it to be the low point. Everybody in the neighborhood is bigger than them. We call AB where the minimum is, and f of AB is the minimum value. So how do we find these things? Well, let's get a definition here. Critical points, you knew that was going to come in here. For a point in the domain of your function, it will be a critical point if both first order partials are equal to 0, or if either partial does not exist. If f of xy has a local extrema at a point AB, and the first order partials at that point exist, then the partials at that point must equal 0. So let's try to find some critical points. Suppose we have this function. I take the partial with respect to x. I get 2x plus y. I'm going to set it equal to 0 and solve for y. So I get y equals negative 2x. Take the partial with respect to y. I get x plus 2y plus 1. I set it equal to 0. I'm going to replace that y in there with negative 2x. And simplify, solve for x. So I get x is equal to 1/3. Plugging that back in over on the right, I get that y is negative 2/3. So my critical point is 1/3 negative 2/3. Now before I go into how to figure out what it is, let's do another critical point. So here's my function. The partial of g with respect to x is 2x plus 2y plus 4, set equal to 0. We'll try this a little bit differently. We'll show you a different way of solving for x and y when you've got 2 equations. The partial with respect to y is 2x minus 8y minus 6, and then we're going to set that equal to 0. What I want to do is find the difference of the 2 equations. Subtract one from the other. So we get 10y plus 10 equals 1, which means y is equal to negative 1. Plug that back into one of the equations. Simplify, and I get x equals 1. So the critical point here is 1, negative 1. Now we want to talk about how to determine if the critical point is a maximum or a minimum or a saddle point. Saddle point's that weird one that was a maximum in one direction and a minimum in the other, because it kind of looks like a saddle. So remember back in Calc 1 when you found a critical point at, say, x equals a, and you realize that if you plugged it into the second derivative, if the second derivative at that point is positive, then your function is concave up, so at that point you have to have a minimum. And if the second derivative with a in it is negative, then your function is concave down, so you had a relative maximum. We're going to try to develop the same kind of thing, but for multivariable. So I want to figure out how to find the second directional derivative. The second directional derivative at the unit vector AB. So I need to take the directional derivative of this new function, f sub x times a plus f sub y times b. Now when I take a directional derivative, I take the partial with respect to x and multiply it by a, and then I take the partial with respect to y and multiply it by b. But there are 2 terms in here, so the first thing I'm going to do is do the f sub x, and then I'll do the f sub y. Now let's look at this. See, when I take the partial of f sub x times a, I get f sub xx, and when I multiply it by a, I get a squared. When I take the partial of fy with respect to x, I get f of yx. And I multiply it by a, so now I have ba. Now look at these other two terms. These come from when I take the partial with respect to y. When I take the partial with respect to y of f sub x, I get f sub xy. I multiply it by b, so now I have ab. And finally, when I take the partial of f sub y with respect to y again, I get f sub yy. I multiply it by another b, so I get b squared. Now recall that f sub xy is the same thing as f of yx, and multiplication is commutative, so ab is the same thing as ba, so I can bring those two middle terms together. So I'll have this. Keep in mind, what I'm doing right now is mainly to show you why this is going to work. I'm not expecting you to generate this on your own. I just want you to try to follow why this works, because now it's going to start getting really gross. I am going to complete the square on this thing. Notice I have an a squared here, I've got an a here, and then I've got some crap over here that has no a in it. So I can complete the square with respect to a. The first thing I do is I'm going to factor out an f sub xx to get this. Now when I factor out f sub xx, notice this 2f sub xy didn't have f sub xx. So because I factored it out, that means I have to divide by it. So to complete the square, I have to take this half of this 2 of fxy over fxxb. So I get fxy over fxxb. And then I have to square it, and I add that. But I can't just add any old thing. I need to subtract on the outside whatever I added on the inside. And this is a little tricky here. Notice I added this expression, fxy over fxxb squared, but on the outside of this expression, I have fxx. So when I try to remember what I actually added, one of those f sub xx's on the bottom cancels out. So what I really added on the inside was just this. So I want to subtract it on the outside. So cleaning this up a bit and giving me some room, I have this. So I completed the square. Let's go ahead and write that as a square. From this other expression, I noticed that the last two terms both have a b squared in it. I'm going to factor out a b squared, and I'm going to factor out a 1 over f sub xx. So what I have looks like this. Why am I doing this? Because I feel like it. I'm doing a proof. Don't worry about why I'm doing stuff. Just follow. Looking at this, I see the a plus f sub x, that first thing where I completed the square, that's going to be always positive. That's always going to be positive because it's squared. And in the second expression, b squared is always positive, and I divide it by f sub xx. So the plus or minusness of this kind of depends on the f sub xx and this expression here. So let's focus on this for a second. I'm going to define d to be that expression, and let's see what we can do with this. Let's say I have x naught, y naught is a critical point, and I want to consider what this expression is. If d is negative, that's only going to happen if the first two, the f sub xx and f sub yy, have different signs. One's positive, one's negative. In that case, I'm going to have concave up in one direction and concave down in the other. It's also possible they have the same sign, but they're not big enough to overcome this f of xy squared, and when you subtract it, you get a negative number. So that means that pull of the f sub xy is stronger than in the x or y direction. So if d is negative, you have a saddle point. What if d is positive? If d is positive, that means fxx and fyy must be the same sign, because that needs to be positive. And it's going to be bigger than the second expression. And I know fxx and fyy, since they have the same sign, I only really need to look at one of them, not both of them. So if fxx is positive, then that means that part of the graph is concave up, which means I have a minimum. If f sub xx is negative, then I have my graph is concave down at that point, and I have a local maximum. That's the tada point. This is what you want to remember, this d. If d is negative, you get a saddle point. If d is positive, check f sub xx to tell you if it's a minimum or a maximum. So let's revisit those two examples at the beginning and see what those critical points were. We had this function f of x. We found the two partials and the critical point. Finding the second order partials, no variables there. I don't have to worry about plugging it in. I calculate my d. I get a 3, which is greater than 0. And I notice my f sub xx is positive, which means At 1/3, negative 2/3, this function has a relative minimum. Let's check the other function. I had my first derivatives. My critical point was at 1, negative 1. When I take the second order partials, I get 2, negative 8, 2. Again, no variables to worry about plugging in. Figure out what my d is. I get negative 20, so I have a saddle point. Let's look at the takeaway. What do you need to know from this? You do not need to remember all that stuff I went through about why this trick is true. What you need to remember is finding the critical points and how to determine if they're relative maxes, relative mins, or saddle points. First thing you do is find all the first order partials and then find the critical points. Once you find the critical points, plug them into D. Once you plug them into D, if D is negative, you have a saddle point. If D is positive, you have an extrema. And f sub xx will tell you if it's a local maximum or minimum. This is the part you want to remember and the part we'll use.